Factoring binomial expressions. Above you can see a list of perfect squares, and obviously it doesn't stop here. How we're able to achieve each one of the numbers in this pattern is taking 1 times 1, 2 times 2, 3 times 3. Now how will that connect to us factoring binomial expressions? I find 14 here, and I also can find 16. Some of you may recognize that it can be that in order to factor this, we're able to actually factor out a numerical value. Others may not recognize that right away. So what can we do? Well, we know that 144 breaks into 12 times 12, x times x, and 16 breaks into 4 times 4. So because I have subtraction, and this is divisible by 2, I may start by writing it with the 12s in front, the 4s in back, 1 addition and 1 subtraction. But if I stopped here, it would be wrong, because you need to recognize that 12 and 4 can still be factored. That means I can still factor out a numerical value other than 1. The largest number I can factor out of 12 that I can also factor out of 4 is 4. So let's factor out 4 out of this first group. 4 times 3 is 12. 4 times 1 is 4. Same thing over here. Let's factor out of 4. 4 times 3 is 12. There's the x. 4 times negative 1 is negative 4. And then the 4's multiply to give us 16. Now we could have achieved the same answer by initially recognizing that a 16 could have been factored out. So 16 divided by 144 divided by 16 is 9. 16 divided by 16 is 1. Then this breaks into 3, 3, x, x. We can keep going, and 1, 1. And so this is how we have a 16 out front. 3 x's are in front, 1's in back. So even if you don't recognize it right away, as long as you recognize once you start putting into factors that you can still divide out a numerical value, you can still achieve the exact same answer. Let's go into example number 2. Example number 2, I have 49 and 9. 49 is breaking into 7 times 7. 3 times 3, this is divisible by 2, so take 6 and divide it by 2 to get 3. Same thing, take 10 divided by 2 to get 5. And how do we know we can keep going? Because with binomials, when we are going to factor binomials, we do need to have subtraction in the middle. Okay, 7 and the x's come from the front, the remaining in front. 3 and the y's come from the back, the remaining back. 1 is addition and 1 is subtraction. 2 more problems for this quick video. 81 and 4. 81 breaks into 9 and 9, 4 breaks into 2 and 2. Now this is where it gets a little tricky. So I've got this, got the perfect squares and I have subtraction, but now I go back and I'm like, oh, both the front and the back both contain x's, and they both contain y's. For those that may like to write them out, there would be 1 x and 3 y's in front, and 3 x's and 1 y in back. Now what's the most I can take out of both of these? I can take out at least 1 x, and I can take out at least 1 y. So 1 x out of the front, and then 1 y, 1 x, 1 y. What does that leave me with? 81, I'm left with just 2 y's in front, and I'm left with just 2 x's in back. So if I did this correctly, when I distribute, I should get 81 x y to the third. I've got that. Negative 4 x to the third y. Exactly. Well, how can we complete this? This, as we set it up above, breaks into 9 and 9, 2 and 2. Each one of these is divisible by 2. So 9's come from the front, 9y, 9y. 2 x's come from the back. 1 is addition and 1 is subtraction. Now here's the part a lot of students are going to forget. Don't forget to bring back down the xy. Our very last problem. We have 25 and 1, great. 5 and 5, 1 and 1, divisible by 2. But notice we don't have subtraction in the middle. So this is not factorable.